welcome back. Let's do some more bouncing ball problems. I'm hoping it's starting to get there. Sometimes we've just got to think through it a little bit, and then it sort of makes sense. And remember, as with all science, practice, 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 and then practice some more. And it's fun. Well, I think it's fun. That's why I teach it. Anyway, so let's move on. Here we go. So I'm going to give you a velocity time graph which describes the motion of a ball that is falling from rest. In other words, initial velocity is 0. Falls from a height of 5 meters. It hits a cement floor and keeps bouncing. And then we've got some parts labeled on the graph. So let's look at the graph. Here's the graph. Now, if you look at this graph looks a little different to the ones we've drawn up till now. Why? Because over here, that isn't a straight line. It's been drawn at an angle. This graph is now taking into consideration the time the ball spends on the floor. We've ignored it when we drew the velocity time graphs before, because generally it's really, really short. So we want to make life a little bit easier for you when we go and we analyze a graph, okay? But this is more accurate because it spends time, okay? What I do need you to see, okay, that's my velocity that it leaves the floor with. What this graph is telling me, okay, now listen carefully to me. Down is negative. We dropped the ball. The ball moved down, and they're showing this velocity as being negative. This is very important. So before I even start any equations, we realize that up is positive, okay? I'm just going to get rid of this part. What we also recognize, this is where it hits the floor. This is where it bounces off the floor, hits the floor, bounces off the floor, okay? At this point, it's at the top of a bounce, and C is where it's spending time on the floor, okay? So this is one of those things where up until now we've told you ignore this, but this is the whole point of the fact that the ball hits the floor, it squishes, and then it unsquishes and bounces off. But it's got to squish and stop, then it can change direction. The things we tell you to ignore, but some of you are going, but that's not what happens when you ignore it. We're not ignoring it this time, okay? So, we've got it. Calculate the speed, direction doesn't matter, that the ball hits the floor with. Okay, so calculate. I can't get it off the graph, actually. So we want final velocity. We know initial velocity is 0. We know acceleration. Now, we've chosen down as negative. In fact, we didn't choose it. We didn't have a choice. Okay, they told us that. So this is minus 9,8 meters per second squared. And we don't know time, but what I do know is delta y. We've now got to think carefully about this. It's dropped from 5 meters above the ground. They said down is negative. That means this is minus 5. That's a biggie here. Looking at the information I'm given, I can't use an equation that has time in it because I don't know time. So again, we're going to use this one. Now, I know some of you are going, how do I know what the equations are? They're on your information sheet. You're not expected to remember them. I know them because I've been doing this for a while, okay? But what you should be doing is working with an information sheet when you study and when you do problems, because then you get used to what it looks like. And really, the more you do this, these eventually will stick, I promise. So we want VF, VI is 0, minus 9,8, minus 5. So this is V squared. Now we're going to have to pay attention to some maths here. So I've got 2 times minus 9.8 times minus 5, and I get 98. Okay? I need to take the square root of this. You know from maths that when you take the square root of a number, you can either get a positive value or a negative value. We've got to look at this carefully because we know it is got to be a negative value. And they actually just wanted the speed. But I'm now going to take the 98 and I'm going to square root that answer. And I get 9,899. You know what? I'm going to keep 3 decimal places just to make it a little bit more accurate because rounding this off will give me 9,9. I'm going to keep it as 9,899. All right, but they wanted speed. Speed doesn't matter about the direction. But speed must be positive. Speed is a scalar. I don't care about direction. Speed cannot be negative. Very, very important there. So now I know what the velocity is at B. Which point on the graph corresponds with the moment when the ball hits the floor for the first time? Here. That's when it's hit the floor. Between B and D, that's where it's spending time on the floor. So that's B. That's all they wanted. No explanation needed. At which point does the ball reach maximum height after bouncing? So here it's bounced, velocity 0, maximum height. That's E. That's straightforward. What happens during interval BD? Now, I've spoken about that a lot during this. During that interval of BD, that's when the ball is on the floor and experiencing an upward force that's going to change the motion of the ball. So it's the time it spends on the floor changing direction. So it's experiencing a force. Now, do you notice I'm not asking you to do anything with time here? Okay? I could if I wanted to, because I know that it hit the floor here at 9,899. Okay? I could very easily turn this into a momentum question because I know what it hit the floor with and I know what it leaves the floor with. I've changed in velocity. However, what didn't I tell you? The mass of the ball. Okay? There's lots of things we can do with these. It gets very exciting. Why is the magnitude of the velocity of D less than the magnitude of the velocity at A? Because kinetic energy isn't conserved. Okay? It's an inelastic collision. Very, very important. Kinetic energy isn't conserved. When you bounce a ball, you hear a sound. Kinetic energy is changing into sound. It's changing into heat because there's rubbing on the floor. Okay? What is represented by the gradient of the graph from A to B? Well, it's a velocity time graph. Gradient of a velocity time graph, acceleration. Specifically, acceleration due to gravity. Acceleration due to gravity. Oh, now they want the height. by height. We know initial velocity when it leaves the floor. We know final velocity when it gets to the top. We know acceleration is minus 9,8. We want delta y. We don't know time. So we would use Vf squared equals Vi squared plus 2a delta y. We know that's 0. So 7,6 squared plus 2 times minus 9,8 delta y. So I'm definitely going to need to put this on my calculator. So 7.6 squared, which I'm now going to put onto this side. So it's maybe I should just pay attention to what my calculator is telling me, because I didn't. Minus 57,76 minus 19,6 delta y. Let's divide by, 19.6. And we get 2,95. There we go, nice and simple. And that's it. Oof. Lots of work, lots of practice needed. Nice section though. So that's the end of this lesson for now, and I will see you again next time.